This is the first of several videos that will show you how to set up a simulation of a line sync in COMSOL. The videos are set up using version 4.2 in COMSOL, and that will show you the various details involved with setting up this model. Now, one of the things that is different between the current version, which is 5.3 or 5.4, and the version 4.2 in the video, is how you start off setting up the model initially. So I'm going to show you how to do that with this current version. So if we start off with the model wizard, then we select 1D. So we want a 1D model, and then we need to select the physics, and this is going to be the physics will be flow through porous media. So we go to fluid flow and select porous media and subsurface flow, and then Darcy's law. And so we'll click on that to select it, and we'll check done down here. And then this is what the model builder looks like. We'll want to set up a study. The study is the solution to the problem, and we select study, and then we go over here, and there are two options: a stationary and a time-dependent study. And we want a stationary study. That means steady state. So we add that, and it appears right here. Okay, so this gives us the basic model builder setup, and now we need to go and set up the geometry and do various other things that are described in the original video. Again, keep in mind that some of the details are going to look a little bit different than this, but the basic functionality is the same, and I think you should be able to translate what you're seeing in the video into this version. Hopefully that'll go okay.
This video will show you how to build just a simple model in COMSOL. The model will be a one-dimensional head distribution in the vicinity of a line sink. This is what the hydraulic head would look like, for example, in the vicinity of an idealized well. So we'll use 1D axisymmetric, and we'll set up the model by using the model wizard here initially. So we'll click next, and we'll use the Darcy's law of physics, and this will be a stationary model or steady state. So we'll select that, and then we hit the checkered flag because we're done with that part. Okay, so this is the model builder. These are the main elements of the model. And we'll go through here, and initially we'll set up some definitions. The variables that we'll include will be put in right. I already set up a file that has the variables in it, so we can navigate here to the load variables from file, and this is the file. This should be saved on the Model Gallery website, so you should be able to get access to this file. And we open it, and here are the variables that we'll use for the problem. Now, the next step will be to go here in the geometry. We'll just really progress from top to bottom, and the geometry that we'll use for this problem is just a line. This is just a 1D problem, so it's very simple geometry. And I just right-clicked, and I'm going to put in this interval. And so the line will be from 0.1 to 1,000. And if I click that button, I build it, and there's the line. So this is 1D axial symmetry. So here's the the axis, and then this line will be rotated around that axis. So really, this is simulating a disk, but the things that are going on in the disk are only changing along this radial line. Okay, so that's the geometry, and we're not going to use materials yet. Darcy's law these are the defaults, and so we go here, and this will allow us to put in the material properties. And we scroll down, and the properties that we need to put in are here. So we can go here and put in user defined. We could type the value in, or we could use a value that is entered as a variable. In this case, we'll use a mix of these techniques, and here I'll just type in the values for the properties of water, and the density will be 1,000 kilograms per meter cubed, and the dynamic viscosity in Pascal seconds is 0.001. Okay, so we entered those in, but what I'm going to do here for permeability, in this case, I'm going to use the hydraulic conductivity, and I'm going to put in a value that I've got here defined as a variable. So if I go back up here to variables, these are these things that I just imported. Right there is the hydraulic conductivity. So what I've done is defined a variable named K that has that value with these units. And so if I go down here to the properties and just type in K, then I will use the value that I defined up here in variables. And let's see, I also need porosity, and porosity, it's not really needed for the analysis that I'm conducting, so we'll just put in a nominal value of 0.1. Okay, one of the advantages of using variables like I've done here is that in some models these variables will appear in several different places, and we can change them all at once by using a variable name and then changing the value right here. Okay, so those are the properties that we need to include. We also need to specify the boundary conditions. And what's done as a default is that the conditions at the ends here are specified as no flow. So if that's what we want, then we don't need to change anything. But it won't be a very interesting problem if that's all we have. So I'm going to put in a boundary condition where I specify the hydraulic head at one side, and I specify the mass flux at the other side. And actually, to be consistent with the example, what I'm going to do is, instead of using mass flux, I'm going to just delete this. I'm going to have the other boundary be an inflow boundary, which will be, instead of a mass flux, it's a volumetric flux. Okay, so these are the two boundary conditions that I've added, this one and this one. And so here's how we set it up. We'll click here on the hydraulic head, and I need to specify the place where the boundary occurs. So that's the hydraulic head boundary, and I select it by pressing that plus there. And so this is boundary number 2, and it's indicated right there. And then don't worry about all this stuff. The value of the hydraulic head that I'm specifying at the boundary is right there. And that's the default, and I'll just keep that value 0, hydraulic head at the boundary. And then the other boundary is the inner boundary. And basically what's happening is we're injecting or pulling water out of this boundary. And so we need to give it a flux. It talks about velocity, but it really wants a flux. And so if we go back here to the variables, we have a term here called well flux. And this is the volumetric flow rate that's coming out of the well divided by the area of the well and the surface area of the outer surface of the well. And so that gives us an average flux. And we'll use that variable name here. So we'll just type that in. And that is our boundary condition. And we have to also select it here, so I'll pick that and plus the plus, and so I have the numerical indicator of this boundary location set up. Okay, so the next step is the mesh, and in this case I'm just going to use the default mesh, and so it puts mesh points on there, and we'll go here to the study and it's ready to run. So I press this equal sign to compute the results, and there are the results shown in the default plot. This is the pressure as a function of distance along the radial distance, the radial length. The units are in pascals, and so that's the profile. Sometimes it's more convenient to look at these plots in using semi-log, and so you can see out here we have a straight line, and we get a little bit of funny business going on here because it's really quite a coarse mesh that we're using. Okay, and so let's change this plot and take a look at, instead of the pressure, let's look at the hydraulic head. So what I want to do is go to this line graph and go here. This is what's being plotted, and I can go and select from a variety of options here. There's the hydraulic head. That's dl.h is the name of the variable. That stands for Darcy's law. .h. So we go there, and then to plot it, we go here, and there's essentially the same data, but we're plotting it now with respect to hydraulic head instead of with respect to pressure. Okay, so this is a nice first start. What I want to do is compare this to the analytical solution. So it's a fairly simple analytical solution for this problem, but we need to get that data in here. And so one way to do this is to create an analytical expression. And so if we go here, go up to definitions, go to functions, analytic, then we can create a function called Theim, and the expression is Q term. This will be a variable that we defined, and a log of R divided by R influence. That's the maximum radial distance, and the arguments we need are Q term, R, and R influence. Okay. The units, we can put those in later. So let's see. I think what we're going to need to do here is include some global definitions, and I'll do that by going to global definitions, parameters, and including this Q as a global parameter, and it'll be minus 0.001, and the radius of influence it's very important to get the spelling correct, and that's 1,000 meters. All right, so here's why we needed to do that. Well, there's actually Q defined right here, so, and radius influence. Okay, so never mind. We're going to take this out. We don't really need it here. And so this should work with what we have. So what we'll do to plot this is have to do is go here to the study and press update solution. That will then, we don't rerun the solution, but by pressing update, what we do is allow the output to have access to this new function that we've just created. And then to plot it, we're going to go to the plot that we're looking at here and right click and put in another line graph. And that'll be plotted over this line. So we'll select that line, and then we'll plot the expression that we just created, and that's a function called Theim. And let me see if we can get access to it here. Okay. I'm going to go here and copy it. We need to give it those arguments. So I'm going to go down here and just type those in, copy them like that. These are all variables that we've created except R, and we'll put this in like so. So we're plotting it with respect to R. And let's see how that works. Okay. So what we're doing is plotting this function, this analytical function that we've just created called Theim as a function of R. The R goes in right there. And the results just plotted on the screen here. Now it's kind of hard to see them because they're really quite close to each other. So we have a little bit of difference. You can see the blue line under there. And so what I'm going to do is to make this a bit thicker and make this one, let's make this one dash or dotted. So this is the analytic expression, the exact, and it's dotted. And what I'm going to do is go here and rename it so I can keep track. Theim analytic. And then I'll go to this one. This line shows the numerical results. I'll make it a little bit thicker so we can see it. And I'm going to change the name to numerical. Okay, there's what we get. So we see that these are actually, I mean, if we look at it this way, they're quite similar. If we look at it semi-log, we see right here at small values of R, the numerical is departing a bit from the analytical. And that's really a mesh effect. We can try making a finer mesh and see how that is corrected. We could also calculate the error between these two solutions and see how the error changes with the mesh.